Welcome to the Deep Dive. Today we're tackling a challenge, really, that sits right at the heart of the digital world.
Uh,
How do we consistently build and acquire these complex software systems that run pretty much everything?
yeah, and maybe more importantly, how do we make sure they actually work and are, secure?
It's the fundamental question, isn't it?
Yeah.
So much relies on this structure that most people never even see.
Mm-hmm.
Absolutely. And to explore this, we're diving deep into a source document that lays out the landscape of information systems acquisition and development. Think of it as maybe the instruction manual for building digital things.
Yeah, a pretty detailed one. Our mission really is to cut through some of that complexity. We want to pull out the essential insights, the real nuggets, to give you a shortcut to understanding this absolutely crucial topic.
It's about uncovering that hidden structure behind the apps and systems you use every day, right?
Exactly.
All right, let's unpack this and figure out what makes a system go from just an idea to something real and hopefully reliable.
Okay, so at the foundation, we're talking about systems development methodologies. Basically, a structure an enterprise uses to plan and control how they develop systems, software, new applications.
And why do they need them? Just winging it doesn't work anymore.
Well, not really. I mean, systems are just getting more and more complex, and businesses need them faster than ever. So a methodology provides that necessary structure, that control.
It's not just throwing code at a wall then. You need a blueprint, a process.
Precisely. And the kind of system you're building often points you toward a specific path. If you're looking at internal, organization-centric applications, things like tracking sales data or making sure you're compliant with regulations.
Where control and structured info flow are key.
Right. You often see more traditional approaches used there, like the structured development lifecycle, the SDLC, or maybe other detailed software engineering methods.
But what if you're building something more focused on the end user? Maybe giving them different ways to visualize data for better decision-making, like a specialized mapping tool or a dashboard.
Ah, okay. Those end-user-centric applications, they're often more about interaction and optimizing performance for individuals. So they might lean on alternative development approaches, maybe ones that are a bit less rigid.
So where does this whole journey usually begin? What actually kicks off a major system project?
Well, the source points out it's rarely arbitrary. It's usually triggered by something concrete. Maybe a new business opportunity you want to grab, or a problem with an existing process or tech that just needs fixing.
Or maybe needing to link up systems with partners.
Yeah, or align with industry standards. That happens a lot too.
And these triggers aren't just technical problems, are they? They're tied directly to business drivers, the things pushing the organization toward its big strategic goals.
Exactly. The document really emphasizes that project objectives need to be SMART.
Specific, measurable, achievable, relevant, and time-bound. That old chestnut.
Right. And using something like a scorecard approach can really help here. It gives you objective evidence to measure the actual business value of the potential system, and it helps prioritize requirements.
Gets everyone on the same page.
Yeah, and helps spot conflicts or dependencies early on, which saves a lot of headaches later.
So setting the stage properly sounds critical. It's not just deciding informally, hey, let's build this thing.
No, definitely not for anything significant. Formal initiation needs clear procedures to communicate the need. That means detailed documentation on the problem, what the desired solution looks like, the potential benefits.
And who gets affected?
Yes, identifying internal and external factors, stakeholders. It's about laying that proper, formal groundwork.
Okay, so the need is identified, it's formally initiated. Now you have to decide how you're going to build it. The document lays out some classic models. Let's look at the traditional waterfall, V-shaped, and iterative models first.
Okay. The waterfall model is maybe the most intuitive if you think about building anything sequentially. You complete one phase, like requirements, then design, then coding, then testing entirely before moving to the next, like water cascading down steps.
This feels like it would work beautifully if you knew exactly what you needed from the very beginning.
And if those needs weren't going to change?
Which happens when exactly?
Rarely. But yeah, it's best when requirements are likely to be stable and really well-defined up front. It forces you to determine the architecture early on. It can even help with things like web apps, where prototyping screens can help nail down requirements.
So the advantage is clarity, a clear template.
Yeah, it provides a clear template for the methods in each step. Requirements gathering, design work, programming, etc.
But let's be honest, what's the big problem with waterfall in the real world?
Well, the big problem is its inflexibility. If something unanticipated happens or needs change, trying to flow backwards up the waterfall is difficult and costly,
And it demands perfect requirements up front.
which is often unrealistic to get from users. Plus, you don't actually see a working system until very late in the game. Users need incredible patience, and the business environment itself might change before you even deliver the thing.
Okay, so the V-shaped model seems like a reaction to some of that. It puts verification and validation front and center.
It does. The V shape in the diagrams visually shows how testing activities mirror the development activities. So, unit testing verifies the code written during programming. Integration testing verifies the detailed design. System testing checks the architectural spec.
And user acceptance testing, UAT, validates against the original requirements.
Exactly. It emphasizes that link between each development phase and a corresponding level of testing.
This sounds built for projects where you absolutely need rigorous testing and assurance that you're meeting requirements, maybe high-risk stuff.
Yes, it's highly disciplined. It ensures verification and validation activities are integrated throughout the whole process. That gives you greater assurance that user needs, and importantly, security controls are met. It's often flagged as particularly good for smaller projects where that level of discipline is manageable.
But the downside, still pretty rigid.
Yeah, the flip side is it's still quite inflexible. It's hard to leverage effectively for really complex projects or those where you know there's a high probability of change. And sometimes that heavy emphasis on documentation might mean less time actually spent on development work itself.
Okay, so if both waterfall and V-shaped are quite structured, what about the iterative model? The name suggests repetition.
It's a cyclical process. You basically develop requirements and build and test the system in repeating cycles or iterations. Each cycle adds features or refines the system incrementally until the whole application is complete.
So you get working software earlier, maybe in smaller chunks, even if it's not the whole picture. This sounds much more adaptable to changing requirements.
It is. It's often considered well-suited for larger projects where you can maybe deliver independent features periodically to users. The big advantage is getting value into users' hands sooner.
What's the trade-off for that flexibility then?
Well, it definitely requires more complex project management because things are constantly evolving. Risk analysis needs to happen more often, and usually by highly qualified people. And the overall project completion date can sometimes be a bit ambiguous early on.
So for you, the listener, understanding these different structures helps explain why some software projects feel like a carefully planned, maybe slow build that could be waterfall. Others feel like a constant cycle of build and test, maybe V-shaped. And some are built and refined, piece by piece, adapting as they go that's iterative. And we'll definitely get to Agile, which builds on this.
Right. Each approach has its place and its own set of challenges.
Let's use the traditional SDLC as a kind of roadmap, though, to understand the typical steps involved in bringing a system to life. Even if you don't follow this exact model, it outlines the general phases.
Yeah, and the names and even the number of phases can vary, but the core ideas are there. And remember, the path changes depending on if you decide to build the software yourself or acquire it from someone else.
Okay, phase 1, the feasibility study. This sounds like the gatekeeper phase, figuring out if the project is even worth doing in the first place.
That's exactly it. The goal is to analyze the problem, explore potential solutions, and build a solid business case. It's not just about listing features, it's about stating the strategic benefits, quantifying cost savings, estimating the ROI.
And looking at softer factors, too, like user readiness.
Yeah, assessing intangible factors like user readiness, process maturity. Basically, can the organization handle this change?
And this is where you make that fundamental call, build versus buy.
Yes, the feasibility study is supposed to determine a time frame, identify the optimum risk-based solution, which might be develop it internally, acquire it, modify an existing system, or use a vendor product. It estimates costs and makes sure the whole thing actually fits the business strategy.
And that build versus acquire decision is huge. What factors into that?
Oh, lots of things. How fast you need it, the cost difference, obviously, whether your own staff have the skills to build it, the ongoing license and maintenance costs if you buy from a vendor, how it needs to interface with other systems, compatibility with your strategic plans and IT infrastructure, how likely future changes are. It's a complex equation.
And the outcome is a report recommending a path forward. The document also mentions an impact assessment here. Is that part of it?
It's closely related. An impact assessment is more specifically about studying the potential future effects of this project on other current projects and resources, understanding the ripple effect, basically.
Okay. Phase 2, Requirements definition. This feels like the real brain-building phase, figuring out exactly what the system needs to be and do.
It is absolutely critical. This is where you specify the business requirements. What should the system do? How will users interact with it? Under what conditions will it operate? What information criteria must it meet? Getting this right is just fundamental.
And crucially, this is where non-functional requirements like access control, security, privacy are defined. This feels like a make-or-break point for security down the line.
It really is. A lot of the security and privacy weaknesses that cause major problems later can be traced back to being overlooked or poorly defined right here. So key activities involve bringing in all the stakeholders, identifying those security, privacy, governance requirements up front, analyzing and resolving conflicts between different user needs.
And translating those needs into something concrete.
Yes, converting user needs into clear system requirements. Using something visual, like an interactive prototype, can be a huge help here to make sure everyone understands. Then you need to record these requirements, formally structured documents, maybe requirements management tools or databases.
So if the feasibility study is the gatekeeper, this phase is building the foundation. Getting requirements wrong here is like building that house on quicksand, right?
Exactly.
Yeah.
Fixing requirement errors later in the process costs exponentially more time and money than getting them right up front.
So verification is key.
Absolutely. The document stresses formalizing requirements and rigorously verifying them. Are they complete, consistent, unambiguous, verifiable, modifiable, testable, traceable? That review process has a massive payoff later by preventing rework and misunderstandings.
And user involvement here isn't just, like, nice to have.
No, it's absolutely necessary. Active involvement from management and all the relevant user groups is crucial to prevent wasting resources on a system that won't satisfy needs. It's also key for getting commitment so you actually realize the full benefits. Without management sponsorship, clear requirements, and user buy-in, those benefits might just never happen.
And the IS auditors already looking closely at this phase. What are they focused on?
Yeah, they're involved. Auditors want to ensure security engineering is considered early and integrated throughout the system's planned data lifecycle, confidentiality, integrity, availability, from creation to destruction. They check that adequate audit trails, which they'll rely on later, are being defined right here. And they confirm that regulatory, statutory, and legal requirements are being properly factored in.
Okay, so after requirements, the path splits depending on that build versus buy decision. If you decide to buy, you go to phase 3A, software selection and acquisition.
Right. This is the process that kicks in after requirements definition if the feasibility study pointed towards acquiring a system. You revisit those build versus buy factors, weigh the risks and benefits, consider your enterprise's capability to develop versus the cost and risk, the pros and cons of total ownership versus vendor dependency, cost differences, availability of generic software, the time gap.
And users are still heavily involved here?
Oh yes. If you're purchasing a package, the user must be actively involved in evaluating and selecting it to make absolutely sure it meets their business needs.
Okay, but if you decided to build it yourself,
Yeah.
you go to phase 3B, design. This is where you create the detailed blueprint.
Exactly. You take those requirements from phase 2 and turn them into a detailed specification for how the system will actually be built. You break the system down into parts modules, components figure out how they interface, define the implementation using hardware, software, network components, includes detailed program specs, database specs, and crucially, security considerations.
This is where things like system flowcharts, entity relationship models for databases, screen designs, report layouts get created.
Yes, all of that. And prototyping is often used heavily here for screens and reports. You define processing steps, computation rules, design the data files or databases, write program specifications, and importantly, this is also where you develop the test plans.
Test plans for everything.
Pretty much. Unit tests for individual programs, subsystem tests, integration tests, interface tests, load tests, stress tests, security tests, backup and recovery tests, the whole gamut. You also plan for data conversion from old systems and do risk assessments of how data, especially personal data, will flow.
The document specifically mentions risks associated with software development. The design phase feels like where a lot of those risks can become very apparent or hopefully get mitigated.
It is. Risks can range from the strategic, like ignoring the overall business strategy, to business or benefit risks, where the system just doesn't meet needs or is a waste of resources. And then there are project or delivery risks.
Like going over budget or missing deadlines.
Yeah, exceeding financial or time limits, issues with suppliers, internal enterprise factors like stakeholder conflicts or politics, the external environment changing, even the technology choice itself can be a risk. But a key insight from the source is that the primary cause of problems isn't usually bad coding. It's often a lack of discipline or using an inappropriate methodology for the project.
And the IS auditors really focused on controls in this design phase, aren't they?
Absolutely. Controls, controls, controls. Are controls being built into the specs? Are they included in the test plans? Are there plans for continuous online auditing functions? They evaluate the design process itself. Are structured techniques being used? Prototyping. Are the test plans adequate? And critically, is there a formal change control process established to prevent uncontrolled changes after the design is supposedly finalized?
Which brings us to a really vital concept the document mentions, software baselining,
Yes, the design freeze point.
like locking down the blueprint.
Pretty much. It's the point where the user requirements are reviewed against the estimated time and cost. Any changes requested after this baseline is established require formal procedures, including assessing the impact and getting approval, often involving a cost-benefit analysis.
And failing to manage requirements through baselining leads to
Scope creep. That classic project killer where requirements keep changing during development, throwing schedules and budgets completely off track. Baselining also marks the start of formal software configuration management, or SCM, bringing all the work products requirements, docs, design specs, test plans under formal change control for the rest of the lifecycle.
how involved are users typically in this very detailed technical design review? Less than in requirements.
Generally, yes, it gets quite technical, but developers still need to be able to explain how the technical design actually meets the functional requirements defined earlier, and stakeholders definitely need to be aware of the cost implications of hardware and software choices made here. Auditors, of course, are very interested in the control implications of those choices.
Okay, moving to phase 4. If you took the acquisition path, it's 4A, configuration.
Right. This applies especially to big package systems like ERPs. Instead of writing lots of new code, you tailor the acquired system to your enterprise's needs, often by modifying configuration tables and setting parameters within the software itself. You might still need to build some interface programs to connect it to other systems, though.
And this sounds like it relies heavily on having strong change management policies in place.
Crucially so. Those policies need to define roles and responsibilities, how changes are classified and prioritized, usually based on business risk, require formal impact assessment, specify authorization and approval processes, often involving both business process owners and IT.
And tracking everything.
Yes, tracking the status of changes, assessing impact on data integrity, making sure changes happen under system or application control, not direct user intervention. It's all about controlled modification.
Okay, but if you took the development path, phase 4B is development. This is where the coding actually happens.
Correct. Based on that detailed design from Phase 3B, programmers start writing the code, debugging it, and formalizing the supporting operational processes. Systems analysts are usually heavily involved here too. And this is all done in a dedicated test or development environment, not the live production system.
Key activities are coding, documenting, debugging, testing programs.
Yes, and also developing the programs needed for data conversion, creating the user procedures for the transition, training selected users, carefully documenting and applying any modifications needed for vendor software you might be building upon so future updates can still be applied. And importantly, identifying and applying secure coding and configuration standards, that whole security by design principle.
The source talks quite a bit about programming methods and techniques. Standards sound pretty important here for quality and maintenance.
Absolutely vital. Program coding standards, how you write code, how you document it internally, declare data, handle input-output, make the code easier for others and your future self to read, understand, and maintain. This is huge for long-term quality and minimizing setbacks if team members leave.
And structured programming techniques.
Like top-down design, modularity, breaking programs into smaller, manageable, logical pieces with high cohesion and low cupping. Coupling these make programs much easier to develop, understand, test, maintain, and enhance later on.
What about tools like IDEs, online programming facility?
Yeah, integrated development environments. They allow interactive coding, compiling, testing. They can definitely speed up development and help enforce standards.
But there are risks.
Sure, you can end up with lots of different versions of code floating around if you're not careful. There's also the risk of reduced integrity through potential unauthorized access or updates if controls aren't strong, and the possibility of changes accidentally overwriting each other. So, strong access control software is key when using these powerful tools.
There's a huge variety of programming languages mentioned too. COBOL, C++, Cante, Java, scripting languages, 4GLs, even low-code, no-code platforms.
Right. It just reflects the diverse technological landscape we'd work in, different tools for different jobs.
And program debugging, finding the errors.
Essential. The purpose is detecting and correcting programming errors, crashes, logical flaws before the code gets anywhere near production. The document mentions tools like logic path monitors to trace execution, memory dumps or traces to see what's happening internally, and output analyzers to compare expected results with actual results.
Okay, phase 5, final testing and implementation. This is the final push before the system goes live for real.
Yes, the main goal here is to establish the actual operation of the new system in the production environment, and critically conduct the final user acceptance testing, or UAT.
This is where the users give the final sign-off.
Pretty much. They test the system in a near live or live environment to confirm it meets their documented requirements and they're satisfied it's ready for production.
And the document mentions that the system might go through certification and accreditation here. What's that about?
Right. That's a formal process, often used in government or regulated industries, to assess the system's overall effectiveness at mitigating risk, ensure management accountability, and establish that appropriate internal controls are in place and working. This typically includes intensive security testing, things like penetration testing, vulnerability scanning, and validating control configurations.
Once the system passes all these final hurdles and gets the green light, migration.
Correct. After successful full system testing and UAT, you migrate the system to the production environment. The date is determined. For really large or complex systems, this migration might be treated as a separate project itself or done in carefully managed phases.
And planning is key.
Absolutely. There should be a formal implementation plan, usually developed back in the design phase and revised as needed. It stipulates all the steps for setting up in production, who's responsible for what, how things will be verified, and critically, it must include detailed backout procedures.
The escape plan.
Exactly. The plan for reversing the implementation and going back to the old system if major unforeseen problems occur during or immediately after go live. You have to have that safety net.
And even after migration, there are still some tests.
Yes, often commissioning tests, especially for interfaces or distributed systems, to make sure everything is communicating correctly in the live environment. And a final check to ensure no test data was accidentally left behind in the production database.
There's a key point mentioned for acquired software. User management, not just the vendor, should coordinate the implementation. Why is that?
It's about control and ownership. To avoid the potential for unauthorized changes or even malicious code being introduced by the vendor during that final, critical step, the user organization needs to maintain oversight.
Site acceptance testing also happens here.
Right. That's the full system test conducted in the actual operations environment, which might be slightly different from the final test environment. UAT is part of this, confirming production readiness and user satisfaction. Security testing, like penetration testing, might also be performed again at this stage.
Okay, the system is live, but we're not done yet. Phase 6, post-implementation review. This is the look-back phase.
Exactly. After the system has been implemented successfully and has been running for a little while, this formal review takes place. Its purpose is to verify that the system was designed and developed properly and that the built-in controls are actually working as intended in the real world.
So you're assessing a few things here. Does it really meet the user requirements and business objectives?
Yes. Are the controls that were defined actually implemented and effective? How do the actual cost benefits and ROI stack up against what was projected way back in the feasibility study?
And identifying problems.
Right. Develop recommendations for any inadequacies or deficiencies found, and a plan to implement those fixes. And importantly, you also assess the development project process itself.
Looking back at how the project was run.
Yeah. Were the methodologies, standards, and techniques followed properly? Were the project management techniques appropriate and effective? It's the essential feedback loop.
For you, the listener, this phase highlights that the project isn't truly over just because the system is live. There's this crucial step to learn from the entire experience, good and bad, to improve future projects.
Absolutely. Continuous improvement.
Now, woven through all these phases, the document really emphasizes the important role of the IS auditor.
Yes. Their function is consistent throughout the entire process. Analyze the risks and potential exposures in each phase, and ensure that appropriate controls are being designed and implemented to minimize those risks cost effectively.
Cost effectively being key controls shouldn't cost more than the risk they're mitigating.
Precisely. Auditors obtain and review project documentation. They often attend team meetings offering advice, not directing. And they assess the project team's ability to actually produce the required deliverables on time and within budget.
And they're looking closely at the project management discipline itself.
Oh, yeah. They check things like the level of committee or board oversight, the risk management methods being used, how issues are managed, cost management practices, planning and dependency management, the quality of reporting to senior management, the effectiveness of change control processes, stakeholder involvement, and the formal sign-off process at key milestones.
Documentation sounds absolutely critical for the auditor.
It is. The auditor needs to see adequate and complete documentation for all phases, covering objectives, deliverables, responsibilities, schedules, dates, economic forecasts, costs. It's the evidence trail.
Now, as we mentioned earlier, the traditional SDLC isn't the only game in town. The document covers several other approaches and concepts.
Right. And the choice of which method to use depends on things like company policy, the knowledge and experience of the developers, and the specific technology being used. And it's important to remember, a programming technique, like, say, object-oriented programming, can often be used within different development methodologies, whether that's waterfall or agile or something else.
Okay, let's touch on prototyping, sometimes called evolutionary development.
This is all about quickly building a working model of the system, or parts of it, often focusing on the user interface first. The idea is to test the design concepts, gather user feedback early, and reduce uncertainty or risk.
And these prototypes can be throwaway or evolve.
Exactly. Sometimes you build a throwaway prototype just to clarify requirements or explore a design idea, and then you start fresh building the real system. Other times, you use an evolutionary approach where the prototype gradually gets refined and built upon until it becomes the actual finished system.
But the document warns about a potential danger here: pressure to implement early prototypes.
Yes, a significant one. Users see something working, even if it's just a mock-up, and they might not understand why it needs lots more work under the hood. This can create pressure to push the prototype into production before crucial elements are properly built, things like robust backup and recovery, security controls, audit trails.
Leading to systems that look okay but are fragile or insecure.
Precisely. It can lead to finished systems that lack essential controls and might have complex, undocumented change control issues because they grew organically rather than being systematically designed. It's that classic trade-off, the potential time and cost savings of prototyping versus the risk of implementing something incomplete or uncontrolled.
Okay, how about rapid application development, or RA?
Gear A is specifically focused on developing strategically important systems quickly while also trying to reduce costs and maintain quality. It does this by using a combination of proven techniques.
Like what kind of techniques?
Things like using small, highly skilled teams, relying heavily on evolutionary prototypes, using powerful development tools, like case tools, which we'll get to, often a central repository for project information, intensive workshops instead of slow back-and-forth communication, and importantly, enforcing rigid time limits or time boxes for development cycles.
So it's fast-paced, uses prototyping heavily, but needs those strict deadlines to keep things moving.
Exactly. It's generally considered good for developing individual systems quickly, but maybe less suited for large-scale, enterprise-wide strategic planning efforts. Prototyping is really its core tool. It typically has 4 stages: concept definition, functional design, development, and deployment.
And then there's the very popular Agile development. How does the document contrast that with traditional methods?
Agile is presented as a fundamentally different alternative to the traditional sequential SDLC. It's highly iterative and incremental think frameworks like Scrum. It operates on the assumption that requirements are often not fully known or understood upfront and embraces the need to flexibly handle changes throughout the project.
Key characteristics sound like short development cycles, constant replanning, less emphasis on exhaustive upfront documentation.
Yes. Small, time-boxed iterations, often called sprints. Replanning happens after each iteration, reprioritizing requirements, maybe adding new ones, adjusting release plans. It tends to rely more on tacit knowledge, the knowledge held by the team members, rather than solely on extensive written documentation.
Teamwork sounds critical.
Absolutely. Small, ideally co-located teams, daily stand-up meetings for quick coordination. Some agile methods even use pair programming. The product manager role often shifts to being more of a facilitator or coach, and detailed planning and control for an iteration are often delegated to the team itself.
So how does it really differ in practice from, say, the iterative model we discussed?
While both are iterative, Agile typically plans only the next iteration in detail. It uses a truly adaptive approach to requirements, not emphasizing managing a fixed baseline the same way traditional methods do. It focuses on proving the architecture works by building actual functionality early and often. Validation happens through frequent build and test cycles, and the process adapts based on frequent inspections and feedback rather than relying solely on predefined, repeatable processes.
Okay, let's switch gears slightly to object-oriented system development, OSD. You mentioned this earlier as a technique, not a methodology.
Right, that's a crucial distinction. OSD is a programming technique or paradigm. It's a way of thinking about and structuring code where you group data, attributes, and the procedures methods that operate on that data together into entities called objects.
So data and behavior are bundled together.
Exactly. It contrasts with older procedural programming styles where data structures and the procedures that manipulated them were often kept separate. OSD uses concepts like classes as templates for objects, inheritance to create specialized objects based on more general ones, messages for objects to communicate, and polymorphism allowing objects to be treated in a general way.
Why is that distinction between technique and methodology so important for our listeners to grasp?
Because you can write object-oriented code regardless of the overall project management methodology you're using. You could be using OSD within a strict waterfall project, or within an agile project, or an iterative one. Understanding that helps clarify that adopting a new programming style doesn't automatically mean you've adopted a whole new project management process. UML, the Unified Modeling Language, is a key notational standard often used with OSD.
Where is OSD commonly used?
It's widespread now. Web development, e-business systems, case tools themselves, artificial intelligence, complex simulations, lots of areas.
Component-based development, CBD. Sounds like it builds on OSD, like building with bigger pre-made blocks.
Yes, it's often seen as an outgrowth or evolution of object-oriented ideas. CBD is about assembling applications from pre-built, executable software packages called components. These components offer specific services through well-defined interfaces.
And these components can talk to each other even if they're built differently.
Ideally, yes, they can communicate regardless of the programming language they were written in or the operating system they run on. There are different types: client-server components, components that run within the same process, standalone components.
The advantages sound potentially huge.
Yeah.
Faster development time because you're assembling, not writing everything from scratch.
Right. Improved quality because components are often pre-tested. Developers can focus more on the unique business functionality rather than reinventing common wheels. It promotes modularity, simplifies reuse, can reduce costs because component development cost is spread across many users.
Supports different environments, a good build versus buy compromise.
All potential benefits. But there are definitely risks too. Lack of mature interoperability standards can sometimes make integration tricky. You're relying on the reliability of third-party software. Integrating multiple components can increase the system's exposure or attack surface from a security perspective. Managing updates from different component vendors can be complex, and licensing issues can arise.
So successful software integration is absolutely key.
It's critical for CBD to work well, and it still requires well-defined requirements and business needs up front to know which components you need to assemble.
Okay, how about web-based application development? The document flags this as significant.
Yes, because it provides a powerful approach for integrating code modules not just within an enterprise, but also between different enterprises. It addresses some of the integration headaches associated with older, specialized APIs.
And it relies on specific technologies.
Primarily XML-based technologies. Things like SOAP, which defines how APIs communicate, often simpler and more loosely coupled than older methods like RPC. WSDL, which describes the specifics of a web service, its message formats, and how to access it. And UDDI, which acts like an electronic directory for discovering available web services.
But the document cautions that the same old development risks still exist.
Absolutely. It makes the point that fundamental vulnerabilities like buffer overflows, which have been known since the early days of programming, are still very much a risk in modern web applications. You need to take a risk-based approach to assessing web app vulnerabilities, identifying goals, figuring out what could go wrong, using experience, and putting those risks in the specific context of web technologies. Your controls need to reflect the development approach used.
What about software reengineering and reverse engineering?
Reengineering is basically updating existing, often legacy systems by extracting and reusing design elements and program components. This is frequently done to support major operational changes or adapt old systems to new environments. Methodologies like business process reengineering, BPR, often involve software reengineering.
And reverse engineering.
That's the process of studying an existing application, piece of software, or product to understand precisely how it works, often with the goal of using that information to develop a similar, perhaps competing system. Methods can include decompiling code or black box testing, testing without seeing the internals.
The advantages and risks there.
Advantages are potentially faster development, reduced SDLC time, and maybe even improving on the original design. The risks are significant, though. You might violate software license agreements or infringe on trade secrets, and the tools used for reverse engineering might have limitations.
Let's move into DevOps and DevSecOps. These seem to be increasingly important concepts, bridging development and IT operations.
Right.
The core goal of DevOps is to integrate development and operations teams and processes, eliminating the traditional conflicts and communication barriers between those who build software and those who run and maintain it. The aim is faster, more frequent, more reliable software releases and operational benefits.
But the document notes this creates new risks.
It does. Adopting DevOps changes the control environment and the overall risk level. Whether it's appropriate depends on the enterprise's climate, risk tolerance, culture, and the scope of implementation. It definitely impacts things like separation of duties, SOD, which needs careful reconsideration in a DevOps context.
And DevSecOps specifically adds the security focus.
Exactly. DevSecOps aims to integrate security practices deeply into the DevOps pipeline right from the start. It's about enhancing security maturity, promoting that security by design mindset, and ultimately reducing vulnerabilities by making security everyone's responsibility throughout the lifecycle.
Business process reengineering, BPR. This sounds like a really significant undertaking, more than just tweaking things. Oh yeah, BPR is about fundamental rethinking and radical redesign of core business processes and associated management systems to achieve dramatic improvements in critical measures like cost, quality, service, and speed. It often involves significant automation, which frequently means removing traditional manual controls. Using ERP systems is often a key enabler for BPR, sometimes called Process Enhancement and Redesign, PER.
What are the typical steps in BPR?
It usually involves defining the areas to focus on, planning the effort, deeply understanding the current process, redesigning it to be, implementing the redesign process and monitoring it, and then establishing continuous improvement. It leads to new priorities, a strong focus on process outcomes, and often new approaches to managing people, technology, information, and external partners or clients.
And BPR team activities.
Things like process decomposition, breaking down complex processes into elementary ones, identifying process owners, documenting detailed process profiles. How long does it take? What triggers it? How often? How much effort? Documenting the baseline as-is processes using flowcharts and profiles. It's very sensitive to the organization's culture, structure, direction, and readiness for change. Management needs to anticipate potential issues.
And the IS auditor concern in BPR is primarily about controls being removed.
That's the main one. Key controls, especially manual ones, might be inadvertently or intentionally re-engineered out of a process during the redesign. The auditor's role is to identify the existing controls, evaluate the potential impact of removing them, and ensure that if preventive controls are removed, management is fully aware of and explicitly accepts the potential material risk that might result. They also review if the BPR aligns with strategy and culture, minimizes negative staff impact, and that lessons learned are documented.
Finally, under these approaches, the document mentions benchmarking.
Right. Benchmarking is presented as a continuous, systematic process for evaluating your own products, services, or processes against those recognized as representing best practices, often from world-class organizations.
What's the purpose? Just comparison.
Comparison is part of it, but it's used for more. Strategic planning, understanding strengths, weaknesses, opportunities, threats, SWOT. Making investment decisions, informing system design or re-engineering efforts, including BPR.
And there's steps involved.
Yes, plan. Identify processes, measurements, data sources. Research. Establish your baseline data. Identify reference partners. Observe. Collect data. Maybe visit partners. Analyze. Summarize findings. Interpret data. Identify performance gaps. Convert gaps into operational goals. Adopt. Translate findings into principles, strategies, actions. Improve. Implement actions, monitor, aim for continuous improvement. Sometimes the observe improve steps might be adapted based on the research findings.
Okay, now to make all this development happen, developers obviously use tools. Let's talk about system development tools and productivity aids.
Yes, these are tools designed to help automate and streamline various parts of the development process. A major category mentioned is computer-aided software engineering, or CASE tools.
These are automated tools supporting different activities.
Exactly. From requirements gathering and documentation, sometimes called uppercase, to detailed design work, middle case, to generating program code or database definitions, lowercase. Some tools, like integrated development environments, IDEs, cover multiple stages.
What are the advantages of CASE?
They can help enforce a uniform approach or methodology, provide central storage and retrieval for design information, and significantly reduce manual effort in documentation and even code generation. They can change the development process itself, sometimes eliminating or combining traditional steps. For example, data flow diagrams or data element definitions created in a CASE tool might directly generate source code.
And IS auditor considerations for CASE.
Auditors need to ensure that proper approvals and user involvement still happen, even with automation. They check that the expected benefits of using CASE are actually realized. A key point is that while CASE aids the design process, it doesn't guarantee the design is correct, complete, or actually meets the business needs. Human oversight and validation are still crucial.
So CASE doesn't replace the need for a methodology.
No, it requires an existing project methodology to be effective. Auditors also look at data integrity between different CASE tools if multiple are used, ensure changes are reflected properly in the CASE data repository, and confirm that necessary application controls are still being built into the system regardless of how it's generated. Security and version control for the CASE repository itself are also critical concerns. Auditors might even use CASE tools themselves for analysis.
Code generators and fourth-generation languages, 4GLs, are also mentioned as productivity aids.
Yes. Code generators, often part of a CASE toolset, automatically generate program code based on defined parameters or diagrams. They help developers implement designs more efficiently. Auditors should be aware of how much code is generated versus manually written.
In 4GLs,
Yeah.
aimed at reducing effort.
Right. They aim to reduce the effort, time, and cost of software development compared to traditional third-generation languages like COBOL or C.
What are their characteristics?
Often more non-procedural, meaning you specify what you want the outcome to be, rather than detailing every single step how to achieve it. Think event-driven or object-oriented styles. They often aim for environmental independence, making applications more portable. They usually provide built-in software facilities for things like screen design, help text, graphics. Many incorporate programmer workbench concepts, like an IDE, and they often have simple language subsets usable by less technically skilled users.
But there's a caution.
Yeah, they might lack the low-level control needed for some very complex or high-performance applications. You have to weigh their benefits against the capabilities of traditional languages for the specific task.
How are 4GLs classified?
The document mentions a few types. Query languages and report generators, these can sometimes be used as audit software. Embedded database 4GLs, often user-friendly but maybe less integrated. Relational database 4GLs designed specifically for working with DBMSs, maybe less end-user focused. And application generators that actually generate 3GL code, which can then be tailored by traditional programming staff.
Okay, shifting gears slightly again. The document also covers infrastructure development and acquisition planning and acquiring the underlying physical or maybe cloud-based IT infrastructure that all these systems run on.
Yes, a really critical task for IT departments. The decisions made here have significant economic and technological impact across the enterprise.
And it's complex because there are so many conflicting requirements.
Exactly. You might need infrastructure that supports modern services-based applications, but also legacy systems. Secure remote access, 24/7 availability. Often, no single platform fits all needs perfectly. It requires a formal, reasoned choice process, typically led by the ICT or IT infrastructure teams.
What are the key requirements for the solution?
It has to align with enterprise standards, provide necessary security and privacy controls, integrate with existing systems, consider industry trends, allow for future flexibility and growth, include technical architecture security, be cost-effective, foster standardization where possible, and maximize ROI and efficiency.
There's a phased approach suggested for analyzing the physical architecture.
Yes. Reviewing the existing architecture, often in a workshop. Then analysis and design. then presenting and discussing the functional requirements, maybe in a second workshop, leading to draft functional requirements.
And vendor and product selection happens alongside writing those requirements.
Yes, those processes often run in parallel. You finalize the draft requirements, discuss them, get agreement. That's really the last checkpoint before you get into detailed sizing and potentially a proof of concept.
The proof of concept, POC, is highly recommended for infrastructure too.
Very much so. It's about proving that the selected hardware, software, and data configurations actually meet expectations, including security expectations, before you commit to a large-scale purchase.
What's the outcome of a POC?
A running prototype system, documentation, test protocols. It's based on the results of the procurement process using a representative subset of hardware, test software, maybe vendor software. It should demonstrate key features: basic security setup, auditing capabilities, specific security measures, secured transactions, installation constraints, performance characteristics, resiliency like failover capabilities, the funding model, data handling. It's a crucial validation step. There are also additional considerations for outsourcing, cloud, virtualization, or regulated industries.
Planning the actual implementation of this new infrastructure also sounds complex, needing coordination.
Definitely. It usually needs a phased approach to fit the new components together and requires clear communication processes with other ongoing projects. You need to understand the vendors from the procurement process, select the scope of requirements for each delivery phase, plan the installation, create test plans. Choosing the right partners is also key. It's an iterative process fed by the requirements analysis. Phases like procurement, delivery, installation plan, installation test plan often overlap.
Can you elaborate on those phases? Procurement.
Procurement involves communicating the business needs, the solution overview, quantities needed, requirement statements. This is where service level management discussions begin, negotiations happen, contracts and SLAs are signed.
Delivery time.
That overlaps procurement. You develop a detailed delivery plan, priorities, goals, timelines. It needs review with all involved parties, likely iteratively.
Installation plan and test plan.
The installation plan is developed cooperatively with everyone affected. The installation test plan builds on that, based on dependencies. It includes test cases, requirement specs, process definitions, measurement info. These require the physical architecture analysis and infrastructure decisions to be finalized.
Okay, let's zoom in on hardware and software acquisition specifics, buying systems from vendors. This requires detailed specifications.
Absolutely. You need specifications, often in an invitation to tender, ITT, or a request for proposal, RFP, to give vendors a clear picture of what you need. And you need predefined evaluation criteria to judge their responses fairly. The specs must define usage, tasks the system needs to perform, specific requirements, and the operating environment.
What kinds of things should be included in those specifications?
A lot. Organizational descriptions, centralized distributed cloud. Information processing requirements, what applications will run, expected workload, performance targets, processing approaches. Hardware requirements, CPU, disk, memory, peripherals, networking terminals. System software needs OS, utilities, databases, communication software. Support requirements, maintenance, training, backups, patching. Adaptability needs upgrades, compatibility. Constraints, staffing levels, existing hardware, delivery dates. Conversion requirements. And of course, cost and pricing structure.
And the actual acquisition steps. It's more than just picking the cheapest.
Much more. It involves checking testimonials or visiting other users of the proposed system, using competitive bidding, analyzing the bids against your requirements and against each other using those predefined criteria, analyzing the vendor's financial stability and support capability, reviewing their proposed delivery schedule, checking the pedigree, avoiding risky gray market equipment, analyzing upgrade paths, evaluating security and control features, assessing performance, maybe through benchmarks or POCs, negotiating price, and very importantly, detailed contract review and negotiation.
What should be in that contract?
Warranties, penalties for non-performance, service levels, and crucially, a right to audit clause allowing you to verify vendor compliance. Finally, a formal report justifying the selection decision.
The document includes vendor evaluation criteria, like in Figure 3.20, things like turnaround time, response time, throughput.
Yes, defining these key terms helps objectively compare vendor proposals on performance and capacity aspects. Workload, compatibility, capacity utilization. These provide a common language for evaluation.
And the IS auditor's role in hardware-software acquisition. Checking the process.
Primarily, yes. Did the process start with a clearly defined business need and hardware requirements? Were multiple vendors considered? Were they compared using objective predefined criteria? Was the evaluation fair and documented?
Let's focus specifically now on acquiring system software, things like operating systems.
Right. IT management needs to be aware of the capabilities of system software to improve business processes, and they need short and long-term plans for migrating to newer versions as they become available.
What issues should be considered when selecting system software?
Similar to hardware, but with software nuances. Business, functional, technical needs. Cost-benefit analysis. Risk of obsolescence. Compatibility with existing systems. Security features and posture. Demands on staff skills and training needs. Future growth potential. Performance impact on applications. And the whole open source versus proprietary software debate.
Again, documentation from a feasibility study is needed.
Yes. The document outlines 4 cases. Getting generic software with no customization, having it customized by the vendor, having it developed specifically by the vendor, or using software as a service, SaaS. An RFP or ITT is developed by the project team, including both technical folks and users, and distributed widely. The goal is the best solution at a cost-effective price.
What are the crucial contents of an RFP for software, like in Figure 3.21?
Several key items. How well does the product fit the requirements? Are you accepting deficiencies or paying for customization? Scalability and interoperability. Can it grow with you? Connect to other systems. Customer references. Can you validate their claims? Vendor security requirements. This is huge. Data protection measures, compliance certifications, incident response, and that right to audit clause again.
Vendor stability is important too.
Absolutely. Vendor viability and financial stability. Availability of complete and reliable documentation. Quality and responsiveness of vendor support. Availability of source code, or at least an escrow agreement if you don't get the code directly. Vendors' years of experience. Recent and planned enhancements. Number of client sites using the software. And critically, the ability to perform thorough acceptance testing of the product before making a final purchasing commitment.
Can you clarify ITT versus RFP again?
Sure, an ITT, invitation to tender, is typically used when you know exactly what product or service you want, like specific hardware models, network gear, a database license. The focus is often primarily on price. An RFP, request for proposal, is used when you're looking for a solution, possibly including services and support like system integration, an ERP implementation, supply chain management software. Here, the focus is more on the vendor's capability, experience, proposed approach, and often involves things like source code access.
And sometimes an RFI comes first.
Right. A request for information might precede an RFP just to gather general information and advice from vendors before you formulate your detailed requirements.
Evaluating the RFP responses needs to be objective, you mentioned.
Absolutely essential. Use objective methods like scoring or ranking against the predefined criteria. Narrow it down to a short list, maybe 2 or 3 vendors. The evaluation methodology should be demonstrably objective, equitable, and fair. Techniques like gap analysis can help compare features against requirements.
And you need minimum requirements defined.
Yes, minimum and recommended software requirements need to be clear. Hardware needed, OS versions supported, specific tools or databases required.
What happens with the shortlisted vendors?
Typically, you'd request agenda-based presentations. Give them scripted business scenarios to demonstrate how their product actually handles your key processes. User group participation here is highly recommended. Check the vendor's knowledge and understanding of your business. Site visits to existing customers can help confirm findings in a live environment. A conference room pilot where your users get hands-on with the software is also very valuable for understanding the system and identifying areas needing customization or workarounds.
The IS auditor encourages talking to current users.
Strongly encourages it. Ask about reliability, service commitment, the quality of training, support, and documentation, overall customer satisfaction. Get the real story.
And then the final selection and contract.
Document the choice clearly. Negotiate the contract carefully, and always have it reviewed by legal counsel.
What are the key contract items for software?
Specific deliverables and costs, delivery dates, documentation, commitments for fixes and upgrades, training provisions, data migration assistance, source code escrow terms, if applicable, installation and customization support, clear user acceptance criteria and the period for acceptance testing, terms for any changes the purchaser might need to make, maintenance agreements, SLAs, software copy allowances for business continuity testing, payment schedule often linked to delivery milestones, confidentiality clauses, data protection and compliance agreements, and once again, that crucial right to ongoing audit. Contract management also includes ongoing status reporting and milestone tracking.
And the IS auditor's role specifically in software acquisition, still focused on security and process.
Yes. Ensure adequate security controls were considered before the agreement was signed. A major risk is acquiring software with inadequate built-in audit trails, weak password controls, or poor overall security architecture. The auditor verifies controls are considered. They review the feasibility study decision, the RFP contents, especially security responses, the vendor selection support documentation, attend presentations or pilots, confirm legal review occurred, check evidence of compliance, like certs, and ensure adherence to procurement policies.
Okay, let's bring a lot of this together by looking specifically at control identification and design. This is how we actually ensure these systems do what they're supposed to, accurately and securely.
Right. IS auditors need a deep understanding of the controls that ensure the authorization, accuracy, and completeness of data as it flows through the system input, processing, and output. They need familiarity with different control techniques and the evidence they produce, like reports, logs, and audit trails.
Application controls are specific to the system's functions, input, processing, output.
Exactly. They are controls designed specifically for those functions within an application. The goal is critical. Ensure that only complete, accurate, and valid data is entered and updated, that processing is performed correctly according to specifications, that the results meet expectations, and that data is maintained accurately until changed through authorized means.
What are some examples?
Things like edit tests on input data. Is it the right format, type, range? Totals that need to reconcile, reconciliations between different processing stages, reports highlighting incorrect or missing data. Importantly, automated controls are often coupled with manual procedures for investigating and resolving the exceptions the automated controls detect.
And the overall outcome of good application controls is?
Data integrity and reliability. You get data accuracy, completeness, validity, verifiability, consistency. This means the systems maintain integrity, functions work as intended, and the information produced is relevant, reliable, secure, and available when needed.
Let's break down controls by area. Input origination controls first, ensuring good data gets in.
Precisely. The goal here is to ensure every transaction is entered, processed, and recorded accurately and completely, and that only valid, authorized information gets processed and processed only once. These controls apply to manual input, machine input, even system output that might be used as input to another process.
Input authorization is key, verifying transactions.
Absolutely. Verifying that transactions are properly authorized and approved before they're entered. Examples include physical signatures on source documents, online access controls restricting who can enter certain transaction types, unique passwords or multi-factor authentication to ensure accountability,
What else?
terminal or workstation identification, well-designed source documents, pre-printed, maybe electronic forms, pre-numbering to ensure completeness, and input data validation routines within the software itself to check for correct format and help prevent malicious input like injection attacks.
What about accountability controls where people are involved?
Separation of duties is classic different people responsible for origination, authorization, verification, distribution. Activity reports can be reviewed to ensure only authorized work occurred. Violation reports track unsuccessful access attempts, who, where, when, and need management review.
Batch controls and balancing sound important for ensuring completeness.
Yes,
Right.
particularly where large volumes of transactions are processed. You group input transactions into batches and calculate control totals before processing.
What kind of totals?
Could be a total monetary amount, a total count of items, a total count of documents, or hash totals, which are totals of non-monetary numeric fields like account numbers, just used for checking completeness. These totals, often recorded on a batch header form, are reconciled after processing. Manual or automated reconciliation is needed, and crucially, follow-up procedures for any discrepancies.
What controls are needed around batching?
Things like ensuring a transaction creates a source document. All documents are included in a batch. All batches submitted are actually accepted for processing. Reconciliation procedures are followed. Errors are investigated and corrected properly, and controls exist for resubmitting corrected items. Balancing types include batch registers, control accounts, and computer agreement checks.
And error reporting and handling. Dealing with bad input.
Also critical. Identifying and correcting input errors, whether they happen during data entry or data conversion. Corrections should ideally go through the normal input processes, be verified and authorized, and re-entered. Different handling methods exist. Rejecting the single incorrect transaction, rejecting the entire batch, holding the batch in suspense pending correction, or accepting the batch but flagging errors for later correction.
What other input control techniques are mentioned?
Transaction logs that record all input activity, providing an audit trail. Reconciliation of data at various points. Good documentation providing written evidence. Formal error correction procedures involving logging errors, ensuring timely corrections requiring approval, managing suspense or error files. Anticipation controls, where a user or control group expects certain data or volumes. Transmittal logs for tracking batches. Cancellation of source documents after entry to prevent duplicates. And input sanitization to clean potentially harmful data.
Okay, moving inside the system. Processing procedures and controls. Ensuring reliability during processing.
Yes, and ensuring the completeness and accuracy of data that gets accumulated in files or databases during processing. Data should remain accurate until it's changed through an authorized process.
What techniques are used here?
Things like manual recalculations on a sample basis to check programmed logic, editing routines within programs that test for data accuracy, completeness, validity during processing, run-to-run totals that verify data values remain consistent as data moves between processing stages or programs, programmed controls designed to detect and potentially correct errors, like checking for the wrong file version being used, reasonableness verification of calculated amounts, limit checks on calculated amounts to catch outliers, reconciliation of file totals performed routinely, perhaps using control accounts or files, and exception reports that identify any data or transactions flagged as incorrect or unusual during processing.
Finally, data file control procedures, protecting the stored data itself.
Exactly. Ensuring that only authorized processing occurs against stored data. The document mentions several controls specifically over data files, like in Figure 3.23,
Such.
before and after image reporting, which helps trace the impact of transactions on data records. Maintenance reporting and correction procedures, ensuring error reports are reconciled, corrections are timely, and there's separation of duties for handling corrections. Source documentation retention policies to enable retrieval, reconstruction, and verification.
Labeling version.
Yes, internal and external labeling on files, physical or logical, to ensure the correct data is loaded and used. Controls over version usage are critical for correct processing. Data file security measures to prevent unauthorized alteration via the application itself. General system security protects against other access.
What else?
One-for-one checking of source documents against process listings, using pre-recorded input where possible to reduce initial errors. Transaction logs, again, recording input activity for audit trails and operational recovery. File updating and maintenance controls, ensuring proper authorization, access restrictions, and audit trails for changes. Parity checking or other error detection methods for data transmission accuracy.
The document also mentions different types of data in files needing control.
Right. System control parameters, these affect how the system or its controls work, so changes need strong control, similar to program changes. Standing data or master files need authorized entry and maintenance, with audit trails. Master data or balanced data containing running balances require strict approval, review, and audit trails. And transaction files, which are controlled through import validation, batch totals, exception reports, etc.
So we've taken a really comprehensive deep dive today, exploring this whole structured world of building and acquiring software systems.
Yeah, we journeyed right from the initial need and the feasibility checks through defining requirements, choosing a methodology, maybe waterfall, V-shaped or iterative, or even embracing more flexible approaches like agile.
We looked at the detailed steps often found within the traditional SDLC, from design and development or acquisition and configuration, right through testing, implementation, and that essential post-implementation review.
And we highlighted the tools that support these efforts, CASE, 4GLs, and so on. And crucially, that pervasive need for controls woven throughout. Controls at input, controls during processing, and controls over the stored data, all aiming to ensure systems are not just functional, but accurate, reliable, and secure.
And how the IS auditor plays that vital oversight and assurance role throughout the entire life cycle.
Exactly.
For you, the listener, understanding these concepts provides that powerful shortcut we talked about. It's the framework, the hidden structure that ensures the digital tools you interact with every single day hopefully work correctly and reliably.
Just think about it. Every app, every website, every internal system you use went through some version of this journey, planned or unplanned, controlled or maybe less so.
Okay. Let's leave you with a thought to ponder on, building on what we've discussed. We saw that different development approaches, like the very structured waterfall versus the very flexible agile, involve distinct trade-offs, predictability versus adaptability, detailed upfront planning versus rapid iteration.
So the question is, how does the need for robust controls shift depending on that choice of methodology? Do those fast, flexible methods like Agile inherently require different kinds of controls than the slower, sequential ones? Or is it more about applying the same fundamental control principles in different ways, maybe more frequently or automated?
What fundamental risk are you perhaps implicitly accepting or actively trying to mitigate when you prioritize speed and flexibility over structure and predictability in software development, or vice versa? Where does security fit best in each model?
Something to consider as you navigate the digital world built by these very processes.